I'm Jonathan Sever from the University of Warwick. I've been parachuted into chairing this final session, and of course we have kept the very best of the presentations for last. Isn't that right?
Of course.
So, the first one is on size segregation in granular fluid flows. Michele.
Thank you. Good afternoon, ladies and gentlemen. I'm going to present an approach to the study of granular fluid flows I developed together with Jim Jenkins. And we tried to take into account the presence of two particle species in our flow mixture. Because before going into details of the model we developed, I just want to give some explanation about the motivation that took us to the study of this kind of problem. I am member of a research center at the University of Trento, which tackles the problem of the hydrological safety of basins in the alpine area. And one of the big problems we have in our area is the study of debris flows. This is a typical debris flow that took place some years ago in the Italian Dolomites, not far from my university. What we can see observing, oh God, I didn't want, oh, it stops. Okay, what we can see looking at this kind of flows is that they are very complex. We see that they usually take place on very steep slopes, so we have to use models that are able to take into account the presence of the slope. We have the presence of water, so we cannot renounce on modeling the interstitial fluid. And we have the presence of more particle species. So in most of the cases, the models that do not take into account the presence of distribution in the size of sediments cannot give good results. The problems related to debris flows are many. We have problems related to the triggering of the flows. We have problems related to the transfer of these flows, so the transportation. And we have problems related to the deposition. What we are going to focus in this talk is the problem of the propagation of debris flows. And we will make the hypothesis of flow in fully developed conditions. So we will not take into account the variation in time of the phenomenon. The main thing that we are going to investigate in this case is the influence of having two or more particle diameters on the total flux of the flow which is propagating downstream. This is because we have the intention to see if the presence of more particle species can enhance or reduce the amount of material that can propagate inside the channel, which is a very important design parameter when we want to work on the safety of river basins. Another thing that we would like to be able to do is the reconstruction of the stratigraphy of the soil that takes place after that this kind of flows stops. So after that, we have the resting of the material that generally takes place on the alluvial fens. This is something that has not taken into account at the moment, but this is something that we would like to investigate in the future. How do we want to study this kind of thing? So which are the methods that we want to employ? Okay, we want to apply a theory which should be as simple as possible, just to have an idea of what are the parameters playing a role in this kind of flows. And we are going to consider two types of particles, so we will have two particle diameters and two particle masses in a flow driven inside a fluid or with a fluid. So we will make the hypothesis of binary mixture, as I have already said. Another simplified hypothesis that we are going to do is considering nearly elastic collisions. We are going to do it according to the theory proposed by Jenkins and Mancini. In order to obtain quite simple equations that can be solved without too big effort, we are going to take into account small differences in diameters and masses. where small differences mean that the maximum diameter does not have to exceed 2 times the smallest one. And this allows us to apply some simplifications to the theory of Jenkins and Mancini that were already introduced by Arnarsson and Jenkins. What we added to the simplification of Arnarsson and Jenkins is the presence of the slope of the channel in order to take into account the effect of gravity in the momentum balance. Another thing that we, of course, need to take into account in modeling this kind of flows is the presence of the interstitial fluid, and in doing this, we follow an approach that has already been introduced by Jenkins and Haynes and by Pasini and Jenkins, but again introducing the role of the slope of the channel, which was not taken into account in the original works. And our scope is the one of being able to describe flows that can be driven in horizontal and inclined channels, and we would also like to be able to study flows that can be driven not only by gravity but also from above, which means that we may have a layer of clear water flowing on top of the flow, which can be translated in the presence of a Shields parameter that, of course, is an important driving force in our momentum balance. Moreover, since these kind of flows are characterized by high density, the standard kinetic theory may fail in describing this kind of flows, so we introduced some modifications to the radial distribution function proposed by Torquato in order to take into account what happens in a dense flow, and we take into account also the scale distance L that introduced Jim yesterday, and that has to be introduced in the energy dissipation balance of the particles. Before presenting the equations, I'm just showing a kind of experiment that we carry out at the University of Trento. This is carried out with one single particle diameter. We are planning to make in the future experiments also with 2 particle species. What I am interested to focus on your attention is the presence of lower layers where we have high concentration and an ordered structure in the flow. So we have a sort of clustering and some chains of particles that are flowing, an upper part where we see collisions, and another part here on top where we have the dominance of turbulence and where we have to take into account, of course, the role of water. And here again 2 snapshots of the higher and of the lower part of the flows, just to show which are the very difficult features of the moving of the particle in these 2 conditions that are both present inside the same flow domain. Let's start presenting the variables included in our models. Of course, we have 2 particle species, so we have 2 diameters, RA and RB, and the same we have to introduce for the masses. Then we introduce 2 parameters, the R and the M, that take into account the variation of the mass and the radii of the 2 species. And as stated before, these 2 quantities should be small in order to be able to apply the simplified equations that I'm going to show later. We have, of course, the need of defining the number densities of the 2 species, which are NA and NB. They are connected to the mass density by means of this simple relation, and of course we can define also the volume fractions. What is more interesting to show is the fact that we have to define a mixture velocity, which is a sort of composition of the velocity of the 2 species in which we take into account the different density of the 2 species. We have to define a granular temperature, which is a measure of the kinetic energy of the fluctuations of the particles. The small u represents the velocity of the particles, while we'll see later the capital U represents the velocity of the fluid. And then after defining the temperature of the 2 species, here I represents A and B, we have also to define a mixture temperature, which was defined assuming the hypothesis of equipartition of energy. So this is something that we already found in Jenkins and Mancini work. The first balance equation we have to introduce is the balance of particle momentum, which is a quite standard equation. We have the gradient of the particle pressure, the gradient of the fluid pressure. We have a term representing the gravity force, and in this term, of course, we have the presence of the cosine of phi. Phi is the slope of the channel, because we have to take into account that the normal to the bed of our flows does not coincide with the direction on which gravity is working. And then we have a term which is very important, which is connected to the turbulent suspension of particles determined by the presence of the fluid and the turbulent fluctuations of the fluid. The closure relations we need involve, of course, the particle pressure, which is defined in a standard form. WO represents the root square of the granular temperature. The term we have more is this 1 minus 3x dr, where x takes into account the number densities of the two species, and this is a term that takes into account the presence of the two particle species. For the radial distribution function, as told before, we use the Torquato expression. And then another thing we have to introduce is an expression for the drag coefficient, which is, of course, a function of the difference of velocity between fluid, capital U, and particles, small u. It depends also on the granular temperature of the fluid, and we have also a term related to the molecular viscosity inside this expression. And then we have the definition of the eddy viscosity of the fluid. This is a turbulent viscosity coefficient in which we used a very simplified expression that is based on the very simple law of the wall, which is not the best way of modeling turbulence in a fluid, but is something that enables us to obtain some simple coefficients and simple expression that can be solved quite easily in order to get to a result. In a similar way, we derive the balance of particle momentum. We have again a term including the drag and a term including gravity, a term including the shear stress of the fluid, and we included also a term here on the right-hand side that takes into account the friction that the flow has on the sidewalls of our experimental channel, or of the real channel we may analyze. We have the closure for the shear rate, which follows the classical kinetic theory, except for the presence, again, of a term that takes into account the presence of the two particle species. We have here the balance of particle fluctuations energy, where we have the diffusive term, a production term, a dissipation term, which related to the particles, which includes, again, the effects of the two particle species, and includes the scale AL introduced yesterday by Jim, and which is expressed in the formula reported here. Then we have the balance of fluid in normal direction, gradient of the fluid pressure, gravity, and turbulent suspension. This term is exactly the same that we found in the balance of vertical momentum proposed for the particles, but with an opposite sign, because, of course, this is a term that transfers momentum from one phase to the other. And we have the longitudinal momentum, which takes into account again the gravity and the drag force determined by the difference of velocity between fluid and particles, where the shear stress in the fluid can be defined as product of the eddy viscosity and the velocity gradient of the fluid. Finally, we have a balance of the fluctuation energy of the fluid, in which again we have production, dissipation, and diffusion of energy. And this balance can be used together with the closure relation for the shear stress and with the equation expressing the eddy viscosity in order to obtain K, which is an expression for the strength of the velocity fluctuations of the fluid. Finally, we have the equation for segregation, including the parameter x saw before, which includes the number densities of the two particle species. This is an equation which is identical to the one in the form to the one proposed by Arnarsson and Jenkins some years ago, except for the presence in in the coefficients of a term that determines the presence of the slope of the channel, which was not taken into account in the original formulation. And after evaluating x, we are able to evaluate the volume fraction of species A and B using these very simple formulas. So putting all the things together, we are able to write a system which is not very complicated, even if long. No, it is a system of 9 equations, but it's a first-order differential equation for which it's quite easy to find also boundary condition. We have the unknowns, which are the concentration of the fluid, the velocity fluctuation, of the particles, the velocity fluctuations of the particles, the flux of energy, the velocity of the particles, the shear stress of the particles, the velocity of the fluids, shear stress of the fluid, the relative density of the two species, and then finally a balance of mass, which is necessary in order to be sure that we are conserving the mass of fluid, of course. And in the case in which we want to study a problem on bumpy bed, we have also to add a further equation I'm not going to talk about because we don't have too much time. We can use this system in combination with a few boundary conditions, which are quite classical. We have a condition on the particle pressure on top, which is connected to the possibility of having ballistic trajectories on top of the flow. Then we have a condition on the shear stress of flow of particles and of water, a condition involving the flux of energy, and again a condition involving the 5 minutes, involving the mass balance. And at the bed, analogous condition, we can impose whether the stress ratio or the concentration at the bed. The results are quite similar. We have to impose the flux of energy of the particles. We impose a zero velocity of fluid and of particles, and again a condition involving a mass balance. I will skip this. And solving this system, it is possible to obtain some results. Here I am showing the results of a granular flow in which we have a single species. These are the graphs reported in blue in the 3 panels. And then the solution in the case in which we have 2 particle diameters having a ratio of 1.1. So RA over RB is equal to 1.1. And the mass ratios are according in order to have the same density of the 2 species. What we observe, applying the same kind of boundary condition, is that in the case of a mixture, we have an increase of velocity. In this panel, we have a representation with the continuous line of the mean velocity and with the dashed line the difference between mean velocity and fluctuation velocity. So the depth increases, even if in the lower part of the flow the 2 solutions are quite similar. We have an increase in the case of the mixture of the total concentration, which is represented by these continuous curves. So we have to compare the continuous red with the continuous blue, which is for the homogeneous case. And of course, this determines a big increase in the particle flux in the problem in which we consider 2 particle species. So same boundary condition, only difference we introduce 2 particle species. we have a flow rate which is more or less 2 times the one we have with a single species. I don't have more results to show you, unfortunately, because we finished this work just a few days ago. I'm just going to give a few points for a discussion. So we notice the big influence of the presence of more particle species on the sediment flux inside our flows. But of course, we have also some limitations. The first big limit is that we have not yet made comparison with experiments. This is something we are going to do in the future. We should be able, in the future, in order to model in a best way this kind of flows, to change the equations in order to take into account also ratios of diameter and mass that are bigger than 2. Another thing we want to take into account in the future is the presence of inelastic collision. Our model works for nearly elastic collision, which means that the coefficient of restitution should not be smaller than 0.8, which may not be very appropriate in the kind of fluid we are studying, especially if in water. We would like to build the bed stratigraphy at rest, and this is all. Thank you for attention.
Go back to where you introduced the granular temperature,
Yes?
the second or third slide. So, what surprises me in all these theories, you may want to comment on that, is that you have one. Oh, you've gone too far. Go forward.
Yeah.
You have one temperature,
Yes.
and you mentioned equipartition. Now, there's an alternative theory by Dufty,
Yeah.
and he introduces 2 temperatures, and then he says, if I let the bed relax, if I let, you do have 2.
Yes.
I have 2 temperatures, yes.
Right, but you only work with the mixture temperature.
I only work with the mixture temperature, yes. This is in order to have a simplified structure of the flow of the equations. Otherwise, the system of equations becomes much more complicated. Of course, this is a simplifying hypothesis.
It's a simplifying assumption, you're saying?
Yeah.
Or is it fundamentally true that there ought to be some form of equipartition? Nick?
I think it's a good question.
we may discuss for the entire afternoon about, I think. The first thing we can do is make some laboratory experiments to see how far this hypothesis
Can be investigated, yeah.
This is the first thing we can do, and then we can see what to do. What I can say is that removing this hypothesis complicates a lot our problem. So.
And would you use Jonathan's PEPT experiment to determine that? Or am I a dishonest broker?
The answer's maybe.
That's the sort of thing we need to know, John.
It is. Maybe one quick one, yes. What are the physical mechanisms for the segregation that you produce?
This is a good question, in the sense that here we are not taking into account the classical mechanical sieving mechanism that is included in the process you also follow. Everything is just based on energy and on velocity fluctuations and on the kinetic theories. So this is also something that I want to investigate in a more deeply way, because some of the results are not convincing me very much, in the sense that what we are finding now in our preliminary results is that we have a migration of the larger particles in the places where we have a smaller temperature, which is something that is not observed in many experiments. So in many experiments we have the larger particles moving in the zones where we have the larger temperatures. So about the physical sense of this kind of theory and the physical ability to reproduce what really happens, I think we will have to think more in the future. So I do not have a good answer at the moment, of course.
Okay, I think we have to move on. Thank